Have you ever wondered how an AI can possibly understand a word it's never seen before? You know, a word like jetpacking or some new slang? Well, it's not magic. It's actually a really clever process of just breaking words down into smaller pieces. And today, we're going to dive deep into the specific algorithm that lets models like Google's BERT do this. It's called WordPiece tokenization.
So this is the big question, right? If a model's training data never included the word jetpacking, how on earth does it make any sense of it? The secret, it turns out, is to stop thinking about words as these single, unbreakable things.
And that crucial first step is called tokenization. Honestly, the best way to think about it is like Legos. Instead of needing a brand new, unique Lego brick for every single object you could possibly build, you just have a set of smaller, more versatile pieces. And with those, you can build pretty much any word you come across.
Okay, so how do these models decide which Lego pieces to create in the first place? Well, there are a few different ways to do it. But today, we're going to focus on one really specific and, frankly, super influential algorithm.
And here it is. Meet WordPiece. This was developed by Google for its huge landmark model, BERT. And the thing about WordPiece is that it's not just randomly splitting words. It's trying to find the most meaningful little bits of words. You could almost say this is the hidden language that AI uses to read our world.
You know, the best way to really get a feel for WordPiece is to just build a vocabulary ourselves right from scratch. So let's do that. Let's walk through the whole process, step by step, and see exactly how this thing learns to read.
The training process is actually a pretty simple but powerful loop. We're going to start with a basic alphabet of characters from our text. Then, for each step, we'll find the absolute best pair of characters to combine, merge them into a brand new token, and then just repeat that over and over until our vocabulary is as big as we want it.
So to do this, we need some text to learn from. We'll use this tiny little collection of words, what's called a corpus. As you can see, words like hug and pun show up a lot, while bun and hugs are a bit less common. This is our raw material.
All right, step one. We split every single word into its most basic characters. But pay close attention to that double hashtag prefix. This is a really key detail. WordPiece uses it to tell the difference between a piece that's inside a word versus one that starts a word. And that context is absolutely vital. So our starting alphabet doesn't just have H, it also has hashtag U and hashtag G, because they mean different things to the model.
Okay, now for the secret sauce. How in the world do we decide which two pieces to merge together? This is what really makes WordPiece stand out from the crowd. So, another common algorithm you might hear about is BPE. And BPE basically plays a popularity contest. It just merges the most frequent pair of tokens it can find. WordPiece is way more sophisticated. It doesn't ask what's the most common pair, it asks which pair, when we combine them, gives us the most new information. It's all about likelihood.
And this is how it figures that out. Now, don't let the formula scare you. All it's doing is calculating a score by taking the frequency of the pair together and then dividing it by the frequency of the first part times the frequency of the second part. So what does that mean? It means the formula actively penalizes pairs that are just made up of two super common individual parts.
I love this analogy. Think of WordPiece as a matchmaker. It's not scanning the room for the two most popular people at the party. No, it's looking for the most exclusive couple. The two that are way, way more likely to be seen together than they are apart. It's hunting for that unique statistical bond.
Let's actually see it in action. In our little corpus, the pair #U and #G is the most common. It shows up 20 times. But #U on its own is extremely common. The formula sees this, punishes it, and gives it a low score. But look at #G, #S. It only appears 5 times, but because its individual parts are less common, its likelihood score is actually higher. And just like that, we have our winner. For its very first move, WordPiece merges #G and #S to create a new token, #GS.
Okay, so we've seen how WordPiece builds its vocabulary by merging the most likely pairs. But how does it actually use that vocabulary on new words it's never seen before? Let's put it to the test.
Now, this is the second really important insight, and you gotta get this because it's kind of a curveball. The logic for using the vocabulary is totally different from how it was trained. We can forget about the likelihood score for now. When it comes time to tokenize, WordPiece just gets greedy. It looks at the start of a word and finds the longest possible chunk it can that's already in its vocabulary.
Let's walk through this with the word bugs. So first, it looks at bugs. The longest known piece it can find at the very beginning is just the letter B. So it pulls that out. We're left with hashtag UGS. Okay, now it looks at hashtag UGS. The longest piece it knows is hashtag U. It pulls that out. And now we're left with hashtag GS. And hey, we know that's in our vocabulary from our very first merge. And there you have it. Bugs becomes hashtag B, hashtag U, hashtag GS.
And here is exactly why this matters so much. If we were using that other algorithm, BPE, which just kind of replays its merge history, the word hugs might get broken down into ho, hashgoose, hashhogs. But WordPiece, with its longest match first rule, would see that hug is already a known token, and it would split it as hug, hashgoose, hashhogs. So same word, different algorithms, and you get completely different tokens.
So, we've been deep in the details, right? But let's pull back for a second. Why does any of this really matter? How does this one choice of algorithm fundamentally change the way an AI perceives our language?
If you're going to remember just 3 things from all this, make it these. First, WordPiece is all about likelihood. It creates a vocabulary of statistically meaningful chunks. Second, it basically has 2 different brains, a training brain that uses that fancy score, and a tokenizing brain that's just a greedy longest match finder. And finally, WordPiece is strict. If it can't figure out even one tiny part of a word, the whole thing gets marked as unknown.
This final comparison chart really drives all the differences home. You've got BPE, which is all about frequency and replaying history, and then you have WordPiece, which is about likelihood and that greedy search. BPE can handle unknown characters one by one, but WordPiece is all or nothing. If it can't solve the whole word, it just throws up its hands and calls it unk.
And all of this leaves us with a really fascinating question to chew on. We've just seen that one of the most basic things an AI does, just reading a word, is completely shaped by a single algorithmic choice. So if the very alphabet an AI uses can change based on its design, how do you think that choice ultimately shapes its entire understanding of our world?